Hi guys, and welcome to this two-part video on the per unit system. I created this video to really explain the natural philosophy behind per unit. Many people find per unit very confusing when they are first introduced to it. This is not only supposed to be an introduction into how per unit is actively used in its mature form, but also how it came about and the sort of philosophy behind how it works. Please view both part A and part B. There's more of the philosophy in part A and then the final application in power systems in part B. So you'll benefit if you go through part A before you go through part B. Enjoy, thank you. So, per unit. Per unit confuses a lot of people, but it's a very basic mathematical principle and can be applied to any calculations. In essence, per unit is expressing a value in terms of another value, as a fraction of another value. This other value is often called the base. So very simply, say if you had a 5-meter ruler and you had a 20-meter ruler, and this is the value we're worried about, and we want to express this 5-meter length of this ruler in relation to another ruler, a 20-meter ruler, which we will refer to as the base value. So it's a very trivial calculation. So the length of our ruler divided by the length of our base, which in this case is 20, so that's 5 divided by 20, which equals 0.25 per unit. So our 5-meter ruler expressed in per unit with a base of 20 meters is 0.25 per unit. But we could have chosen any value to be our base value. We've chosen 20 meters, but we could have easily have chosen 40 meters. So we have a 40-meter ruler as our base. And then our 5-meter ruler in per unit with a base of 40 meters would simply be 5 divided by 40, which equals 0.125 per unit. And then if a value is in per unit, you can perform all the same calculations you could or would want to do to the real values, this 5-meter ruler value, as long as all of these base values, like the 20 meters, are obeying the same mathematical formula or mathematical relationships as you would be using for the real values. You're then free to do exactly the same calculations you would with the real values, but in per unit, as long as all the bases are linked by the same mathematical formulas or relationships. So let's take a quick example. Let's ask, what is the potential energy increase of a system, of this system, should I say. And the system, just to run home the point that per unit is a general mathematical principle and isn't exclusively used by power systems engineering, even though that's where the mainstay of where per unit is used currently, especially before the advent of computers. Per unit was used a lot in power systems engineering, and we'll get on to explain why that is and the benefits of per unit of the per unit system. But in short, the per unit system was used a lot and is to some extent still used in the power systems engineering because there's a lot of arduous calculations that need to be performed, and using the per unit system makes these calculations a lot more simple and trivial and a lot less arduous. So it's really a mathematical tool to make the calculations simpler, even though they could always be worked out with the true values. But we'll come to a good example which shows how the per unit system makes power system engineering calculations simpler, but first we'll just discuss a more general example, and it also runs home that the per unit system is a general mathematical principle, and it isn't confined to power systems engineering. You can apply it to any mathematical problem. So let's say, what is the potential energy increase of this system? And this system is just simply a slope with a ball, and you want to push this ball up the slope to the plateau. And so how much energy do you need to put into this system? How much more potential energy has the system increased by doing this? And let's say, for the sake of argument, that the height is 20 meters and the weight of the ball is 18 kilograms, and very close to Earth but not quite correct, we'll say that gravity is 10. Now, first thing we need to decide is what equation defines this whole system. What equation are we going to use to describe this whole system? And it's a trivial one that most of you will be aware of. It's potential energy equals mass times gravitational force times by height. And it's a very trivial example. You could very quickly and easily calculate yourself just with the real values. But as an example for per unit, we're going to put the all these values into per unit, perform the calculation, and then convert from per unit back to real values, and show that if you're performing calculations in per unit, you'll get exactly the same real values at the end as if you were to do it all with the real values. So first things first, we need to convert it into per unit, we need to decide some bases for all of these quantities. And we always need to arbitrarily choose all the variables apart from one. So we could choose to arbitrarily define potential energy, mass and gravity, and then we'll use these three base values to calculate the fourth base value. Or we could equally choose to define arbitrarily mass, gravity and height bases, and then calculate the final base of potential energy. We always basically arbitrarily define them, just as before. We can use any values we choose, and except for the last one, which is going to be defined by the calculation itself and the other bases. So for this example, we will randomly pick a say a mass base, and we'll make that 5 kilograms. Then a gravity base of, let's say, 10, and a height base of, let's say, 5 meters. So just as before, we need to convert these values we've been given into per unit, and but before we do that, we will calculate our final base, which is the potential energy base, because we might need that later. And just to follow this equation, so it's the base of our mass, which is 5, times by our arbitrarily decided value of gravity base, which is 10, and our free choice of height base, which is 5 again. So that would be 250 joules is our base for potential energy. And then we need to convert these three values into their per unit using these bases. So to start with, we will calculate the mass in per unit, which is 18 divided by our base mass, which is 5, and that equals 3.6 per unit. So that is the mass of our ball in our per unit system, given these bases which we've defined arbitrarily, but they still obey this rule. That's the only condition. And then our gravity in per unit is relatively trivial because the value is 10 and our base is 10. So that's just going to be called 1. And our height in per unit is going to be 20 divided by 5, which equals 4. So that's our height in per unit, our mass in per unit, and our gravity in per unit. Now we have the system in per unit, we can then go and calculate our potential energy. So we would use exactly the same formula, but we'd use our per unit values. So our potential energy in per unit is equal to our mass in per unit times by our gravity in per unit times by our height in per unit, which is, our mass is 3.6 in per unit, our gravity is 1, and our height is 4, which equals 14.4 per unit. So that's our value of potential energy. And this can then be, now we've got our final answer, we've worked out our potential energy, but it's in the per unit system, so now we just need to convert that back to a real value, and that's simple enough. So our potential energy in a real value is simply our potential energy in per unit times by our potential energy base, which we have already calculated earlier. It's 250 joules. So it's 14.4 times by 250, which equals 3,600. So that's how many joules our system is increased by in a real value. So that is the we're attempting to calculate, because we're tasked with attempting to calculate the potential energy of this system. Now, just to check that these values calculated using the per unit system are exactly the same as what they would be if you calculated it for real, we can just do a quick check. And we can just use the same formula, this formula, and therefore EP equals mass, which is 18, times by gravity, which is 10, times by 20 meters. And if you did that calculation, you would find that this also comes to 3,600. So you'll notice that's exactly the same value as what we got if we're calculating it with real values, as is exactly the same as when we converted it into per unit and calculated it and then converted it back. Obviously, you'll notice in the system, using the per unit system here is actually more laborious than just using the real values. But the advantages of the per unit system will become apparent later. This is just an example of how per unit can be applied to any basic calculation. We'll run through one more quick example. We'll run through a quick, simple DC electrical example just to show you that it can be applied to any system, this per unit way of working. So let's say if we had just a basic cell, basic battery, and we say it's 10 volts, and we have an unknown resistor, we can call it R1. It's just like school. And we know the current, we're given the current, say 2 amps. And the question is, what is the resistance of R1? Yeah, again, this is a very trivial example. And the equation that defines this system is very simple. It's just Ohm's law. V equals IR. And you could just plug in these values and work out R after a little bit of rearranging very simply. But again, we'll use the per unit system just to show that it works and that you get exactly the same values as as when you use the real values. So first things first, we need to define some arbitrary bases. So let's define V base equals 20 volts, but we could choose anything. I base is 8 amps. So now we have a V base and an I base, and there's 3 variables here, so we've defined 2 of them, and the last one is defined by the equation that describes the system. So we've got 2. The third one, R base, is defined by the system, which is going to be V base divided by I base, which is 20 volts divided by 8 amps, which equals 2.5 ohms is the base value. So next step is to convert the system values we've been given into per unit before we conduct our actual calculations in per unit. So voltage in per unit is 10 divided by 20, because our value is 10 and our base is 20, and that's 0.5 per unit. And then our current in per unit is 2, because that's the value, 2, divided by our base, which is 8, and that is 0.25 per unit. So that's our current in per unit and our voltage in per unit. Now we can actually calculate the resistance in per unit using these per unit values, which would be using exactly the same Ohm's law equation here. So with a little bit of rearranging, R per unit is voltage per unit divided by current per unit, and that will be 0.5 per unit divided by 0.25 per unit, and then that will equal a resistance for a resistor of 2 per unit. And then the final step, now that we've calculated our target value, will be to convert that back to a real value. So resistance in ohms is the resistance in per unit times by the resistance base, which is going to be 2 per unit times by 2.5 base, which equals 5 ohms. So that is our final value. And again, we can quickly check that. So if we're going to work out with just the original values, which R equals voltage divided by current, that'd be 10 divided by 2, and again, we come to 5 ohms. So it shows that converting the system into per unit, then doing the calculation, and then converting it back into real values provides you with exactly the same values as if you were going to do it with the real values. Okay, in these examples, using per unit is a lot more laborious than using the real values, but we'll come to some examples when using per unit is a lot more simple than using the real values, especially in power systems engineering. So here's our last trivial example. Let's combine our 2 earlier examples, one about raising the potential of something. In this case, we'll use a pump pumping water, and we'll apply an electric circuit as well. So what we're trying to find is how much water in kilograms the pump pumps. And let's take, say, a 60-second snapshot, and we'll say the gravity is 10 again. We'll say the height that the pump is pumping the water up will be, say, 20 meters. And we'll use a 10 volt source and supplying 2 amps as well. Right, so we'll just quickly draw that. So here is our pump, and it's pumping water up to a reservoir. That is 20 meters high, and is connected to a circuit with a cell again of 10 volts and a current of 2 amps. Now, we first need to decide what are the equations that are sort of defining our system. Where it's a bit of a combination of the last one, it's exactly the same two basic equations. Well, it's not exactly the same because we're going to work out the power used by the pump rather than resistance. So we're going to use P equals IV. That defines the sort of circuit component of the problem. And the other equation that's going to define the rest is, we won't use power, we'll use energy equals IV times by time. And that defines the circuit part of the problem. And then, as the same as before, potential energy equals mass times by height times by gravitational force. So these two equations capture this whole system, and then the bases, we get to choose any arbitrary base for any of these variables. Well, they're bases, as long as they obey these two equations. So we'll actually choose, out of all the variables, there's one identical variable in both, which is energy. So we've got 1, 2, 3, 4, 5, 6, 7 variables. So we can arbitrarily choose 6 and define the 7th from the equations. So first things first is to choose our arbitrary bases. We'll start by choosing arbitrary bases for our circuit part of the problem. So let's say our voltage base is 20 in this example, and our current base is, let's say, 8 in this example, 8 amps. To make our lives easy, we will choose a time base of 60 seconds. So these are bases. And then if we're using this equation here, we've chosen 3 bases, we'll have to calculate the fourth from the others. So our energy base will therefore be 20 times by 8 times by 60 seconds, which will equal 9,600 joules. And that's our energy base. Right, so then we need to put our circuit values, the 2 amps and the 10 volts, into the per unit system. So our voltage per unit equals 10 divided by 20, which equals 0.5 per unit. And our current per unit is 2 divided by 8, which is 0.25 per unit. And then we can, and our time per unit is relatively trivial, because that's 60 divided by 60, which equals 1 per unit. And then we can use this equation up here to work out the energy used by the pump in this circuit. So energy in per unit is 0.5 times by 0.25 times by 1, which equals 0.125 per unit of energy used by the pump in 60 seconds. So we've basically done the calculations we need for the circuit bit. Now we need to move on and address the pump bit of the circuit, which is defined by energy equals mass times height times gravity. So as before, we've got to obey these two calculations with our bases. So we've already defined energy base, so we need to carry that across, otherwise this won't work. So our energy base is 9,600. We'll be using that again. But there are 4 variables in this. One's been defined or carried across from the other, and therefore we need to define 2 further ones and calculate the last one. So let's define G, as usual, as 10. G base, sorry. And our height base, let's make it 2 meters this time. That will mean then we have to calculate our mass base. So we just rearrange this equation. We know that base, we know our height base, we know our gravity base. Well, we made them up and we inherited that one from the last equation. So our M base will equal E base over H base over G base, which is 9,600 divided by 2 times by 10, and that comes to 480 kilograms for our mass base. Now that we have our mass base, we can go on and transfer these few values into our per unit system. So our gravity per unit is 10 divided by 10, which equals 1, trivial enough. And our height per unit is 20 divided by 2, which equals 10 per unit. Now we've got everything we need in the per unit system, we can carry across this energy value into the physical bit of the non-electrical part of our problem, using these per unit values, and calculate the amount of mass in per unit that has been pumped, or mass of water. So the mass of water in per unit that's been pumped is the energy per unit divided by the gravity in per unit times by the height in per unit. And this is just the rearranged equation that describes the physical bit of our problem. So in our case that is 0.125. Energy in per unit was provided by the pump. We got that from the physical part of the problem, electrical part of the problem. We calculated it here, the energy expelled by the pump. And these two were given, and we just converted them into per unit. So it's 1 for gravity and 10 per unit for height, and that equals 0.0125 per unit. And that's the mass that we have pumped with the pump over 60 seconds. And so now all we've got to do is convert that mass in per unit to a real mass value, which is our mass in per unit times by our mass base value, which is 480 480 kilograms times by 0.0125 per unit, which equals 6 kilograms. That is our final answer. as with the last two examples, this would have been easier to calculate had we just calculated with the real value straight away and not put it into the per unit system. But again, we can show that the per unit system calculates the value perfectly accurately, and we will very quickly check it. So voltage 10 times by current 2 times by 60 seconds means that the pump was provided with 1,200 joules worth of energy. 1,200 joules of energy divided by gravity at 10 times by height of 20 meters equals 6 kilograms. So as you can see, the two values are perfectly identical. One worked out in per unit, and then, well, converted to per unit, calculated in per unit, and then transferred from per unit back to real values, and one just using real values. Okay, the per unit method is a lot more complicated and laborious, but it proves that the per unit system can be applied to any problem. So in general, if the base values are all related by this, you can just transfer any values for any calculation into per unit, as long as the base are following the same mathematical rules that are governing the whole system. And exactly the same calculations can be performed as you would with real values. That is the whole premise of the per unit system. It's stating a value as a fraction of another value, and you can then use these fraction of other values, these per unit values, to do any calculation as long as the base values are all obeying the mathematical rules of the system, and the base values are all carried across. So now you've seen some basic per unit calculations. We'll go on to explain a power systems example where using per unit is actually makes the problem a lot simpler to calculate, rather than these where the problem's been made more complicated by using per unit. The main reason why per unit makes power systems engineering problems more simple is that it helps get around having to keep changing voltage and current due to the existence of transformers on the network, because most power systems, well, pretty much all power systems have transformers on them, and switching voltage and current laboriously as you work out the flows across whole networks with multiple transformers can be avoided as long as you convert everything to per unit, and we'll discuss that in the next video.